For years, the entire tech world has been completely obsessed with just one piece of silicon, constantly asking which single chip is the absolute fastest. But when we look at the reality of modern AI today, that question is entirely obsolete. Welcome to This Explainer. Today, we are unpacking Google's 8th generation Tensor Processing Unit, the TPU, to reveal how the AI chip war has fundamentally transformed into an all-out infrastructure war. Seriously, the era of the single chip benchmark is completely dead. True performance now relies entirely on full-stack system efficacy. Just think about the stark difference between isolated flops, the raw math capabilities of one single processor, versus what Google calls the AI hypercomputer paradigm. AI performance isn't constrained by one chip anymore. It's actually determined by how you orchestrate software, hardware, cooling, and networking so they all work together like one massive single organism. To understand this massive paradigm shift, here's our roadmap for today. We're going to explore why workloads must split, dive into Google's specialized TPU designs, the V8T and V8I, examine their revolutionary networking topology, and then impartially compare their strategy against the broader market. All right, part 1, splitting the AI workload. Let's look at exactly why one chip just isn't enough anymore. So the crucial point to understand here is that building an AI model requires massive, uninterrupted data ingestion. But actually talking to that AI, that demands ultra-low latency for instant token-by-token reasoning. Think of pre-training as the phase where the AI goes to school. It sits there, reading the entire internet, mapping relationships over these prolonged cycles, which obviously requires immense bandwidths and continuous uptime. But the reasoning phase, like when you're actually prompting the AI for an answer, is totally different. It generates answers one token at a time, so it needs ultra-low latency to instantly remember the context of your specific conversation. Because these two distinct workloads demand entirely different things from the hardware, trying to do both on a single one-size-fits-all chip just creates massive inefficiencies. So Google actually physically separates these bottlenecks. They fundamentally bifurcate the unified data pipeline into two distinct chips, the V8 for the heavy lifting and the V8I for the rapid response. Moving on to part 2, the V8T, the massive AI factory. This is all about unprecedented scale and throughput. When you're baking a massive new AI model, you don't just need a fast computer. You need a full-blown factory. And the V8T is exactly that. We're talking about linking 9,600 chips together with an absolutely astonishing 2 petabytes per second of memory bandwidth. To put that into perspective, it's just a mind-boggling amount of data flowing instantly. Plus, by using native FP4 support, which is a 4-bit floating point format, it represents parameters using way less memory. This effectively doubles the computational efficiency for those massive matrix math operations. In short, this thing is built to ingest petabytes of data without ever stopping to take a breath. But here's the catch. Standard cores totally choke when fetching scattered data from massive datasets. Imagine a gigantic library where a standard processor has to sprint around, pulling scattered books off random shelves one by one. It's an absolute organizational nightmare, right? It creates massive memory friction. So to solve this, Google introduced something called the sparse core. It basically acts like an ultra-fast, dedicated librarian. It fetches this irregular memory flawlessly in the background, ensuring those main compute ends are literally never starved for data. Okay, part 3. The V8I, the instant call center. Now let's talk about ultra-low latency serving. So now we pivot to the inference phase. This is where millions of us users are typing away expecting instantaneous answers. Ever wonder why your AI sometimes takes so long to reply? Well, the bottleneck actually isn't the speed of the math. It's the time it takes the AI to retrieve its own intermediate thoughts from memory. When you ask a complex question, the model has to constantly remember everything you've said previously. This is known in the industry as the KV cache. And if the chip has to keep reaching out to distant memory banks just to fetch that context, that's when you experience that noticeable, annoying lag in the text generation. So how do they fix it? Well, to master this context window, the V8I actually sacrifices some pure compute density to embed a massive 384 megabyte SRAM scratchpad directly onto the chip itself. It's a brilliant trade-off. By keeping that context literally right next to where the math is happening, it completely eliminates the wait time for external high-bandwidth memory. It guarantees a zero-friction fetch. It perfectly mirrors the philosophy of fast response systems that are built from the ground up for ultra-low latency. But wait, what happens when a modern AI model is simply too massive to fit on just one chip? I mean, if chip A has to sit there waiting for chip B to finish its thought during some complex reasoning, the whole system just stalls out. Well, enter the collective acceleration engine. This is a dedicated background engine that autonomously syncs those intermediate states instantly across multiple chips. It virtually eliminates that collective latency. And the best part, it does it without ever taxing the primary compute cores. All right, moving into part 4, the network is the computer. We are literally rewiring the physics of data. Okay, so to make thousands of chips operate together as one cohesive brain, you kind of have to bend the rules of physical distance. In older 3D torus structures, data had to physically jump through up to 16 different chips just across the pod. But the new Dragonfly topology, it drops that maximum connection path down to just 7 hops. So the physical distance and the time required for any one chip to sync with any other chip is radically reduced. At this scale, the individual chip becomes completely irrelevant. The cluster itself is the sole unit of compute. Think about it like this. No matter how incredibly fast a master chef can chop vegetables, if the ingredients aren't brought from the fridge in time, the entire kitchen stops. Traditionally, the CPU acts as this sort of middleman waiter, slowly fetching data from storage and feeding it to the accelerator. But TPU direct storage bypasses that slow CPU bottleneck completely. It allows these hyper-fast cores to natively pull data directly from the solid-state drives, ensuring they are continuously fed and never left waiting. And that brings us to our final section, Part 5, 2 paths to AI supremacy. It's Google versus the broader modular market. When we impartially look at the broader market today, we're seeing 2 vastly different philosophies tackling the exact same physical bottlenecks. On one hand, you have Google pursuing this closed-loop, top-down vertical integration. I mean, they designed the TPU, the networking fabric, the compiler, and the Gemini model itself. This achieves unmatched cost of performance for their controlled, specific internal workloads. But on the other hand, a company like NVIDIA takes a universal bottoms-up approach. They're building a horizontal, modular ecosystem that connects distinct GPUs, CPUs, and DPUs via standard interconnects, completely designed to serve any model from any company across the entire AI landscape. So, what does this all mean? Ultimately, the crucial takeaway from this explainer is that the battle is simply no longer chip versus chip. It's a battle of entire architectures. As AI algorithms continue to rapidly evolve, the underlying infrastructure must physically morph to match them, which leaves us with a massive question. Which overarching philosophy is truly going to dominate the AI era? Will it be the hyper-specialized, vertically integrated factory, or the broad, horizontally modular ecosystem? Thanks so much for joining us as we unpacked the physical future of artificial intelligence.